Okay, welcome, final week, final 4 days. We're almost done here with chapter 16. And in chapter 16, we've been talking about acid and bases. We talked about sort of the basic Bronsted-Lowry definition of an acid and base. Again, a Bronsted-Lowry acid is something that will donate an H plus, while a Bronsted-Lowry base will accept an H plus. And remember, as we've been talking about, H plus and H3O plus is essentially the same deal. Basically represents sort of the acidic part of the solution. We also talked about that as a result of sort of this definition, there's like partners or bases that are sort of are pairs that are connected to each other. So we typically will have our acid and base on the left-hand side of the arrow, and then really our partners on the other side are the conjugate acid and the conjugate base. And again, the relationship is the acid on the left-hand side is related to the conjugate base on the right-hand side, and the base on the left-hand side is related to the conjugate acid on the right-hand side. And again, because the Bronsted-Lowry definition is an acid will donate an H plus over, that is again the only difference there can be between those sort of pairs for those things to be considered pairs. As the acid donates its H plus, it will have one less H plus when it goes to the other side and becomes the conjugate base. When the base accepts the H plus, it will have one more H plus on the conjugate acid side than it started with because it accepted it. Remember, as well as we talked about that positive charge there on the H plus is important in terms of the overall charge of sort of what happens with our conjugate acid or conjugate base. So you do have to take the charge into account as you're sort of gaining a H plus or losing an H plus. So when you gain an H plus, again, you become one more positive in terms of the charge. And if you lose an H plus, you become one more negative in terms of the charge. So you want to make sure you do adjust sort of those charges. We talked about Kw, which is an equilibrium expression for water, which is equal to the concentration of H plus times the concentration of OH minus. And that equals, for the purposes of our class, pretty much in most classes, a pretty constant number of 1 times 10 to the minus 14. And what this allows you to do is, again, if you know either the H plus concentration or the OH minus concentration, you can basically figure out the other concentration from it. And again, really the H plus is kind of the acid part of the solution. The OH minus is the base part of the solution. So it is really the same calculation regardless of what you're calculating. You're going to take 1 times 10 to the minus 14 divided by the other concentration. And this is one way that you can determine, for example, if a solution is acidic, basic, or neutral by comparing the H plus concentration to the OH minus concentration in the solution. And again, if the H plus concentration is larger than the OH minus, then it will be acidic. If the H plus concentration equals the OH minus concentration, it will be neutral. And if the H plus concentration is less than the OH minus, it will be basic. Remember, the relationship between H plus and OH minus is as one goes up, the other goes down. So that is sort of our relationship. H plus concentration increases, the OH minus concentration decreases, and vice versa. And another very more common way that we oftentimes will figure out acidity, if it's acidic, basic, or neutral, is to use the pH. And the pH is equal to minus the log of the H plus concentration. Remember, again, the pH scale runs from 0 to 7 to 14. Less than 7 is acidic. Above 7 is basic, and neutral there at a pH of 7. And the name does tell you, as we talked about, sort of what you need to calculate it. You do need pH, so you need the H plus concentration or the H3O plus concentration, which is the same thing. There is a similar scale where it is known as the POH, and It's basically calculated kind of the same way, except that it also tells you what you need. So pOH, you need the OH minus concentration, and it's minus the log of the OH minus concentration. The relationship between those two is a nice one. pH plus the pOH equals 14. So this does give you a variety of ways that you perhaps can solve a problem. If you are given, for example, the hydroxide concentration, want the pH, you could calculate the pOH and basically subtract 14 and you'll have the pH. Or you can still use, again, Kw and figure out the H plus concentration and then go into the pH sort of formula. So that's sort of your option there. Remember that as we kind of roll through some of these sort of formulas here, depending on the calculator you're using, you want to make sure that you are punching it in correctly, either kind of forwards or backwards. And you definitely want to make sure you're using your exponent. Last couple of things we talked about there was that if you had the pH, you could get directly from that the H plus concentration, and that will equal the inverse log of the negative pH. And again, on most people's calculators, when you do the inverse log, it oftentimes will kind of pop up a 10 and a caret on your calculator. You want to make sure you make it negative. Again, to get to the inverse log on most people's calculators, top left corner, the shift button or the second button, and then usually the log button that has like a 10 to the x, usually kind of above it. That's usually on most calculators sort of how you can kind of hit that. Also, if you have the pOH, you can get directly from that the hydroxide concentration. Pretty much the same calculation, except obviously it's the inverse log of the negative pOH. And again, when you punch that in on your calculator, it usually kind of looks something maybe like that as well. Any questions on any of that stuff there? All right, so I think this is where we're at. All right, so a couple of examples here. We want the pH, the pOH. Let's do this here. Let's do, for the first one, let's do pH, pOH. Let's also do the H plus concentration. And is it acidic, basic, or neutral? And for the second one, let's do the pH, pOH, H plus concentration. And is it acidic, basic, or neutral? All right, so take a few moments, grab a calculator, make sure it works. Yes. Okay, so let's take a look. So looking at the first one, we have the H plus concentration given to us. So since we're going to be looking for, I guess that would be OH minus we're looking for here since that's the H plus. So since we have the H plus given to us and we're looking for everything here, we could solve for really either the OH minus by using Kw, or we could just get the pH. So it is your choice. Here, I'm going to go with pH first. So I'm just going to go right into the pH here. Negative log of what was given to me, 3.6 times 10 to the minus 9. A reminder that depending on your calculator, if you have a display calculator, that is the negative button, that is the log button. 3.6 exponent button, negative button, and 9 and equals. If you have a non-display, you're going to start with the number, go 3.6 exponent button, negative button, and then 9, and then you're going to hit the log button and then the negative button for a non-display. Either way there should get you here about an 8.44 for our pH. At this point, again, you have a couple of options. Since you do have the pH, you can very easily get the pOH by taking 14 minus the pH. So that's going to give me 14 minus 8.44. And that's going to get me a pOH of 556, looks like. And once again here, still have an option for our OH minus, either using Kw, or because you also have now the pOH, you could do that the hydroxide concentration is the inverse log of the negative pOH, which again on your calculator at 10 caret negative 5.56. And if If you do that there, we got inverse log, right? Hit that negative 5.56. And looks like 2.8 times 10 to the 1, 2, 3, 4, 5, 6 minus 6, I think. And does need a molarity there. And at this point here, we also can determine that it is basic in this case, as the pH is above 7. Any questions on that there? We also talked about sig figs and pH. So 2 sig figs in the concentration, 2 decimal places in the pH, and obviously going backwards 2 decimal places, 2 sig figs going in that direction. Again, to do this calculation in your calculator, just to remind you, if you have a display calculator, again, you're going to do your second or shift button, your log button, your negative button, and 5.56. For non-display, you're going to start with the 5.56. You're then going to make it negative by hitting the negative button. You then will hit your second or shift button and your log button. And you should end up with the right answer in that case. Any questions on any of those there? All right, taking a look at number 2 there, which I got rid of what it was. What was the concentration there? Looks like 9.2 to the minus 2. So 9.2 to the minus 2. Thank you. Now, in this situation, we have the hydroxide concentration given to us. So once again, we could use Kw to get the H plus, or we could just get the POH. So I'm going to go POH first. So POH going to be negative log of 9.2 times 10 to the minus 2. And maybe hit the right button would work probably better there. 9.2 negative 2. There we go. Looks like a 1.04 for the POH. That means that our pH can be found very easily by taking 14 minus the POH. And that's going to give us a pH of 1296. And again, here, like I said before, you could use Kw or you can use the inverse log method. Again, here, just to throw back here, we'll go the Kw method. H plus would be 1 times 10 to the minus 14 divided by 9.2 times 10 to the minus 2. And we'll end up with here. Looks like 1.1 times 10 to the minus 13 molar. R, again, you could do H plus inverse log of the negative 1296. Should also get you there as well. Any questions on that? I guess this would be a 12.96 would be basic as well. Yeah. Any questions on any of those there? Reminder, calculator will not give you perhaps it in scientific notation and stuff like that. So you might have a bunch of zeros when you look at it. All right. So continuing on here, let's do this again. The pH of the solution is 5.67. What's the POH? What's also the H plus concentration, OH minus concentration, and is it acidic, basic, or neutral? So take a few moments there and calculate that up. Okay, let's take a look. So again, here we have the pH. So definitely could get the POH pretty easily. We're just going to subtract 14 from it. And that will get us a POH of 8.33. Now, in terms of the H plus and OH minus concentration, now that we have really both the pH and the POH, we could solve for both. So again, the H plus concentration will equal our inverse log negative pH, which in this case will look something like this, most likely on your calculator. 10 to the caret negative 5.67. And again, that's going to get us here too many zeros to count. Let's see. We got 2.1 times 10 to the minus 6. Again, it does need molarity as it is a concentration. Really, at this point, it opens up another option for you. You could, at this point, use Kw to get the OH minus if you wanted to, or you could do the same calculation for the hydroxide. So again, you have a couple of options on this one. So minus the log, inverse log of negative POH, 10 to the negative 8.33. And we got 4.7 times 10 to the minus 9 molar. Or as I mentioned before, alternatively, you could have just did your Kw divided by the H plus concentration. We should do it that way. Any questions on that? This is going to be based off the pH here, 5.67. Less than 7 is going to be acidic. Yeah. Any questions on those there? Okay. All right. We'll just deal with this question asked then. The pH is 3.14. What's the H plus of the solution? Okay, so we have the pH here, and directly again from the pH, we can get the H plus concentration. So again, it's going to be that same calculation, inverse log negative pH. So 10 carat, make sure you make it negative 3.14. It looks like we will end up with 7.2 times 10 to the minus 4 molar. Once again, 2 decimal places on our pH, 2 significant figures there in our answer. Obviously, this is acidic with a pH of 3.14. Any questions on that? Again, obviously, may not give it to you in scientific notation on your calculator. Yeah, so probably looking at 0.00072 or so. All right. One last one here. POH is 5.67. What is the hydroxide concentration? All right. So again, here with the pH given to us, we can directly get the hydroxide concentration from it. And again, here the hydroxide will equal the inverse log of the negative POH. So something like that. And again, if you punch it in, whichever way you need to punch it in there, 2.1 times 10 to the minus 6 molar in this particular case here. Any questions on how to calculate pH, POH, H plus, OH minus? Obviously, you need to be able to do those. Again, just make sure you understand how to punch it into the calculator. It's usually the issue for everybody a lot of times. All right, the next thing we're going to talk about is up to this point when we're calculating pH or POH or whatever it may be, a lot of times we've been given really just sort of generic concentrations, like you're given, hey, what's the pH if the H plus is this, or if the OH minus concentration is this. Now, it is possible that you may come across a question where you are asked the pH of a strong acid or really even a strong base where you're not given just like the H plus and OH minus in the concentration, but you're given a formula of a strong acid or a strong base. And remember that when we talk about strong acids, we had a list earlier on, but there's sort of that list of 6 sort of strong acids: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydriodic acid. And again, you may be given an actual formula of any of these sort of acids. Remember, in terms of our strong bases, group 1 or group 2 on the periodic table that has hydroxide in it. So kind of like group 1 or 2 with hydroxide, like sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. Now, because again, these are strong acids, or even if we're talking about bases, They are strong bases. They are going to 100% break apart in solution. They're not going to stay together. And that's really important. For example, here, if we did look at something like hydrochloric acid, when we do have hydrochloric acid solution, it will break 100% apart into H plus and Cl minus. And again, you're going to have 100% of these ions floating around the solution. You're really not going to have any of the HCl units together. Now, when we're talking about pH in this situation, which is negative log of the H plus concentration, it is this H plus concentration that's actually the most important thing to try to figure out. And the good news is, as we talked about, for example, in terms of molarity and concentration, we could kind of figure out the concentration of the ions from the concentration of the acid in this particular case. Now, when we're talking about a strong base, like say something like sodium hydroxide, it also is a strong electrolyte, which will break apart into a sodium ion and a hydroxide ion. And in terms of the pH here, we are interested in the H plus concentration, but there really is no H plus concentration in a base, but there is hydroxide. And hydroxide is important because if you know the hydroxide concentration, you could calculate the pOH, and from the pOH, you could really get yourself to the pH. So if you're dealing with a strong base, it's kind of the same idea, except that you'll have the hydroxide concentration, which means you need kind of like an extra step. You actually have to get the pOH first, subtract 14 to get to the pH. If you have a strong acid, you could go pretty much right into the pH equation. So let's just say, for example, we had a 0.1 molar solution of HCl. We wanted to know what is the pH of that. So again, we could use the fact that hydrochloric acid is a strong acid, will completely break apart into H plus and Cl minus. And as we talked about with concentrations, if this whole thing is 0.1 molar, it is a 1-to-1 relationship between that and the H plus. And that means that the H plus concentration in this solution would be 1 times 0.1 or 0.1 molar. And that's really what we need to calculate the pH. At that point, we could then go right into our pH minus the log of 0.1 molar. And that's going to get us our pH here of 1, which we would expect is acidic, definitely, since it's a strong acid. Now, if we were doing the exact same thing with sodium hydroxide here, let's just say we had a 0.1 molar sodium hydroxide solution, we wanted the pH. We would kind of approach it the same way. We would do like we did above there, that our sodium hydroxide, being a strong base, going to 100% break apart into ions. And as I mentioned before, when you're dealing with bases, you don't have H plus, but you do have hydroxide, and that's really what you're interested in. And it's also, in this case, a 1-to-1 relationship between them, which means that the hydroxide concentration would be 0.1 molar as well. But the important part of this is to remember that, again, that is not the H plus concentration, but that is the hydroxide concentration. So what that's going to allow you to do is actually calculate the pOH. It's going to be minus the log of 0.1 molar. That's going to give you a pOH of 1, not a pH of 1. And from that, you can now calculate your pH by subtracting. And you will end up with a pH of 13, which makes more sense since that is a strong base, and we would expect a basic pH. So sometimes you're not given, again, just a generic H plus or H3O plus concentration or OH minus. You're given an actual formula of an acid or a base. And what I would say is, in this class, you're pretty lucky in the sense that we don't talk about how to get the pH of a weak acid or weak base. So if they give you a formula, you probably could safely assume it's going to be strong. And you just basically need to figure out the H plus concentration if it's an acid, or the OH minus concentration if it's a base. The other nice thing is most of the strong acids are monoprotic, which means they only have one H plus, which means pretty much the concentration of the acid will be the concentration of the H plus. It's going to always be kind of like a 1-to-1 relationship. So you'll always sort of have that. I would say with the bases, you might have to be a little bit more careful, especially bases that come from group two, because you typically will not break apart into a one-to-one relationship, but in most cases, that is the case. So let's take a look at it here. Why don't we try these two examples? What is the pH of 0.025 molar perchloric acid and 0.025 molar calcium hydroxide? So take a few moments to figure out the pH of each of these. Both strong, yeah. Okay, so let's take a look at the first one. So we want the pH of 0.025 perchloric acid. Once again, this is going to be a strong acid. And again, what that means is when we have this solution, it will not stay together and will completely break apart into H plus and a little perchlorate here. And really it is, again, the H plus is important here for the pH. And we do know the concentration of the whole thing. We do kind of our mole-to-mole relationship there. It is a one-to-one relationship. So one times it will still give us the same. So the concentration, as I mentioned earlier, a lot of times with our strong acids, since they are monoprotic, it will be pretty much the same concentration across the board there. Now we have the H plus, we could go into our pH, and that's going to get us here a pH of, looks like a 1.60. Which is acidic, which is good since that is a strong acid, so that does make sense. Any questions on that one there? Second one is calcium hydroxide, so that is OH minus with somebody from group 1 or group 2 on the periodic table, which also would probably indicate that this is going to be a strong base. So it will break apart here, and once again, when it breaks apart, it will make a calcium ion and it will make two hydroxide ions, which is kind of important. Again, here we're going to be looking for the hydroxide concentration to help us get to the pH eventually, but first the POH. We do know the concentration here is 0.025 molar. Again, in this case, it's a 1-to-2 relationship, not a 1-to-1 relationship. So to get the proper concentration of the hydroxide, you do need to multiply that by 2. And that's going to get you the proper concentration here of the hydroxide, which is 0.05 molar. Now that you have the hydroxide concentration, a reminder that you could calculate the POH, not the pH, minus the log of 0.05. And that's going to get us here a 1.30. Now, again, if for some reason you thought this was the pH, it should not make sense to you because that would, if that was the pH, it would be acidic, and this is a base, so those things shouldn't make sense. So we could get to our pH really easy by subtracting 14. And if we do that, we will end up with a 1270 pH, which does make sense, and that is definitely a basic pH, which again was what we were expecting in this case. So as I mentioned a second ago, I would say more so probably the bases. You may have to adjust the hydroxide concentration, especially again if it's with somebody from group 2. But most of the time, you'll probably hit those acids that are sort of a one-to-one relationship, which is not too bad. Any questions if you're given an actual acid or base? Yeah, correct. Because when this goes into solution, for every one of these guys, you get one calcium and you get two hydroxides that will come off. And that means it's twice as concentrated in terms of hydroxide concentration. So you just multiply the whole concentration by 2 to get the proper. Yeah. What's that? You do, so that will give you the concentration of the hydroxide. But to get to the pH, you got to first go, ran off the board there. You got to go first to the POH. And then from the POH, you can get to the pH at that point. Yeah. Where you would do the minus the log. Yeah. Other questions? All right, the last thing we're going to talk about are buffers. Why not? A buffer is a solution that basically can resist pH changes, really big pH changes, when you add an acid or a base to it. So sometimes when people learn about buffers, they have a misunderstanding of what a buffer is. Sometimes they always think buffer is like a neutral solution, and that's not necessarily the case. You could have a buffer that's acidic, you could have a buffer that's neutral, you could have a buffer that's basic. You could pretty much make a buffer at any pH range you want, or any pH sort of value that you want. So what a buffer is whatever the pH of that solution is to begin with. If you decide to add more acid to it or more base to it, it should be able to resist changes. It'll be able to maintain it. So if you made a buffer at a pH of 5 and you added some acid, it should hang out around a pH of 5. It shouldn't drop from like a pH of 5 all the way down to 1. It should be able to resist really big changes in the pH. Now, a buffer is made out of special things in a sense in order for it to actually work correctly as a buffer. A buffer is made out of a combination of one of two things. You can either make it out of a weak acid and the salt of its conjugate base. Now, this is your Bronsted-Lowry definition, basically. An acid and the conjugate base, the only difference is an H plus difference. So it's basically the same thing that we talked about earlier. It's called a salt of its conjugate base because, frankly, it's got a spectator ion hanging out there doing nothing, like a sodium, a potassium, something like that, usually. Or you could make a buffer out of a weak base and the salt of its conjugate acid there. And once again, the difference between both of those sides is, again, that Bronsted-Lowry definition of just the one H plus. Now, one thing that you cannot make a base out of is a strong acid or strong base. So if you have a strong acid or strong base and you're like, this is my buffer, the answer is no, that is not your buffer. That is a solution of a strong acid or a strong base. So you cannot make or have a buffer that's composed of a strong acid or strong base. So if there's a strong acid or a strong base, that cannot be a buffer. Now, why is that? It's really for that reason because the way a buffer works is it has to have an acid part in the solution and a base part in the solution at the same time. So you have to have actually both of these things listed up here in the solution at the exact same time. So you have to have an acid part of your buffer and a base part of your buffer, or a base part and an acid part. Both of those things need to be in the solution to begin with. The reason a strong acid or a strong base cannot do that is if we took something like hydrochloric acid, which is a strong acid, and we wanted to make a buffer out of it, what would happen is it would break apart in solution to H plus and Cl minus. And when we look at this solution, we would have basically H pluses around and Cl minuses, which means this is really our acid. This is our conjugate base in this case. And when we look at our solution, the only thing we have there is the conjugate base present. We have no acid part because it's a strong electrolyte. It's going to completely break apart. And this is why this would fail really miserably as a buffer, because it only has one of the components you need in the solution to be a buffer. Now, if you took something like, and we'll do a different one than everybody's favorite example, we will do HF and sodium fluoride. Now, HF is a weak acid. And by the way, I know it's a weak acid because it is not one of those six that we just talked about. That's a strong acid. And this is his conjugate base here. And this is really the salt of his conjugate base. Now, sodium fluoride is actually a salt. It's an ionic compound. And really, when sodium fluoride's in solution, it does not stay together. It breaks apart into a sodium ion and a fluoride ion. And it's actually the fluoride ion and the HF that is the buffer. And if you look at those two things, you can see that the only difference between the HF and the F minus is our Bronsted definition of an H plus. Is the only difference between them. The sodium there is just hanging out. It's really not doing anything. It's just kind of floating around. It's a spectator ion. It's not doing much in terms of it being a buffer. Now, why does this work and the other one doesn't? It works because this is a weak acid, which means it's a weak electrolyte. And that means that when you have a solution of this, because it's a weak electrolyte, if you remember when we did like net ionic equations, total ionic equations, that means that this solution will have HF guys floating around. It will also, I'll put the arrows in that you might not have in the beaker, but we'll put some arrows in the beaker there. It's a weak electrolyte, which means it will break apart a little bit into H plus and F minus. And I'll just take one of those guys out there so we can see it. So what's going to happen in this situation is because that HF is a weak acid, it will set up this equilibrium and it will keep HF in solution. It will also produce some F minus. And if you were making this buffer, you would increase the F minus by adding a little bit more, like sodium fluoride to it to kind of buff up the F minus. But what that's able to do is now what you have in the solution is you have HF, which is like the acid part of our buffer, and you have F minus, which is our base part of our buffer. And that's really important for how a buffer is able to function. Over here, as I mentioned before, with our HCl, which is a strong acid, you only get like one part there. You just get the base part left over in the solution. You don't have that acid part, and it's not going to be able to really resist big changes in pH because of that. First off, any questions on that there? So how does a buffer sort of function? Let's talk about how it works. So let's talk about how it works here in a non-buffer situation. So if we take water, which is not a buffer, and if we take to water over here, got some water, and we add our HCl to it. When we do that, because HCl is a strong acid, it will, as we've been talking about, 100% break apart into ions. And what you're going to have in that solution of water that you just added HCl to is you're going to have a bunch of H pluses floating around and Cl minuses floating around. Now, really important is in this situation, you just created, as you can see here, a lot of free H pluses really quickly by adding that to water that's not a buffer. And what we know about our pH equation is the pH here is equal to minus the log of the H plus concentration. So as my H plus concentration spikes because you added HCl to it, my pH is going to drop a lot. So in this particular case, maybe your water started at a pH of 7, who knows, and you added some HCl to it, it will go from like a pH of 7 down to maybe like a pH of 2 or 1, a really big drop in the pH because you added a lot of H plus to the solution very, very quickly. And that's going to cause the pH to, in this case, basically drop. Now, what happens if we take to the same water here, which once again, not a buffer, and we add sodium hydroxide to it, which again is a strong base. So if we add sodium hydroxide here to water, again, not a buffer, it also, as we've been talking about, will 100% break apart into sodium ions and hydroxide ions. And that means in this solution, you're going to have a lot of sodium ions floating around, which is not that big of a deal. But what is a really big deal is you are going to have a lot of free floating hydroxide ions floating around in this solution. So you will end up with a solution that has a lot of free OH minus concentration or ions floating around in the solution. And you may say to yourself, why is that important for pH? Well, remember again, our pH is equal to minus the log of the H plus concentration, which means in this particular case, you just did something that spiked up the concentration of your hydroxide. And because hydroxide and H plus are related to each other, what that's going to do to the H plus concentration in that solution is you're going to see a big old drop in the H plus concentration. And because of that, you will now have more hydroxide in that solution than H plus. And like we talked about with KW, more hydroxide than H plus, pH is going to jump high. You're going to see a big rise in the pH because of the influx of free OH minus in that solution. And again, maybe it starts at a pH of 7, you add some sodium hydroxide, you end up at a pH of 12 or 13, a really big sort of jump in the pH because you basically just flooded that water with a bunch of free OH minuses. Remember, it is the free H plus concentration or OH minus concentration that ultimately determines the pH of the solution. So by rapidly increasing either of those, you will see a big change in the pH, either up or down, depending on which one you did. Any questions on what happens in a non-buffer situation? So by contrast, let's talk about what happens in a buffer situation. So let's say we added these exact same things to that buffer, and we'll use the one I did because it's less things to write. Everybody likes acetic acid and sodium acetate, but we'll go with this one because it's less things to write. So this is my buffer. And once again, there is basically, this is my acid part, and that's my base part. And remember, again, it is the F minus here, that's the really functioning part of it. And here obviously is the HF, that's the functioning part of the acid part of the buffer. So when you put this buffer into a beaker, it will set up that equilibrium of HF, H plus, and F minus flowing around. And as I mentioned earlier, that's going to allow in the solution, which is my buffer, the base part of my buffer and the acid part. So now you have a buffer that has an acid component and a base component to it. And that's really important for how it's able to function. When you now take that same acid, you take that HCl, which is basically going to be H plus and Cl minus going in for a swim. What's going to happen when you add that H plus to this solution, you're going to get a reaction that's going to occur. The HCl, which is an acid, will actually go and react with the base part of the buffer. So it's going to react with the base part of the buffer. If you remember, they're called acid-base reactions. So if you add an acid to this buffer, it will go find the base part, which is sodium fluoride, and it will do a double displacement reaction where these guys are going to switch partners, basically. And when they switch partners, you will make HF, and you will make some sodium chloride in this case. Now, two things happen here that always happens when you make or you have a buffer and you add something to it. We actually made part of the buffer. And that always happens. So because a buffer has an acid part and a base part, it will use up some part of the buffer, but will make the other part of the buffers. So it's almost sort of regenerating part of the buffer as it does this reaction. The other thing that we made here is sodium chloride. And as we talked a little bit about, you could trust me, it's a neutral salt here. It's not going to do anything to the pH. It's actually what we don't see here that we did see when we looked at it with water. That's really important. It's what we don't see that we did see with water. So if we go back here, when we did this to water, when we added the exact same HCl to it, it generated all that H plus. But when you add that same HCl to this buffer, you end up not seeing any free H plus. And that means that the H plus concentration does not change all that much. And because the H plus concentration stays relatively constant, the pH will also stay relatively constant as well. So what happens in this situation is when you add this, that H plus that normally would come in will actually go and find the F minus, and they will make part of the buffer. And what that essentially does is it does not allow that H plus to remain free in the solution. And because it's not free in the solution, that H plus concentration remains constant and the pH remains relatively constant. I say relatively constant because if you actually followed this and did this, you would actually see the pH go down a little bit, but it will not go way down. So say your pH started at 5 here, your pH may drop to like 4.9, 4.8. It won't go from like 5 all the way down to 1. It will be able to remain relatively constant. It will come down just a little bit, but you won't see the big change. Any questions on that there? Now, if we take the same buffer that has our HF set up in it with our acid part and our base part of our solution, and we add our sodium hydroxide in, that's sodium and hydroxide going in for a swim. We are also going to get a reaction that's going to occur when we add our sodium hydroxide to our buffer. It is a base, so it will react with the acid part of the buffer, which in this case is HF. And it will do an acid-base reaction, which is also a double displacement reaction. And it will make sodium fluoride, which is part of the buffer, and it'll make our friend water. Water is definitely not going to screw up the pH. And sodium fluoride was part of the buffer to begin with. But again, it is actually what we don't see here that we saw when we added the sodium hydroxide to water is when we added to water, we made a bunch of free OH minus. Here, we do not make free OH minus, so we do not see any free OH minus. And what that means is the concentration of OH minus stays relatively constant. And because H plus and OH minus are tied to each other, the H plus concentration will stay relatively constant. And lastly, that means the pH will also stay relatively constant. So because in this particular case, what happens is we do not allow that free OH minus coming in from the sodium hydroxide to just freely be floating around. It gets tied up. It keeps the H plus concentration constant because the hydroxide concentration is constant. So what's going to happen in this case is this guy is going to come in and react with the acid part, and it's actually going to make water in this case. And again, not allow the hydroxide to be freely floating. And that's what allows the pH to remain relatively constant. So a buffer, because it has an acid part and a base part to the buffer, it's able to, when you add additional acid or base to your buffer, stop H plus from being formed in the solution when you add acid, prevents OH minus from being formed when you add base. And that keeps whatever the H plus concentration was in that solution relatively the same. Because remember that when we started, before we added anything, we had a little bit of H plus in that solution. And that original concentration of H plus will remain the same after you add acid or base if your buffer is made correctly and works properly based on what you're adding. Any questions on that? So to summarize sort of a buffer and how it works, typically you take a buffer and you basically want to make a buffer that has about equal parts of the acid part of the buffer and the base part of the buffer. And in the case of our example, HF and F minus basically. Now, when you add acid, to your buffer. It's going to use up some of the base part, but it's going to make some of the acid part. So dramatically drawn here, the acid part of the buffer will increase. The base part of the buffer will decrease when you do that. And if you added base to this buffer, it will react with the acid part and make more of the base part of the buffer. So you'll make more of the base part. You'll use up some of the acid part of the buffer. And again, it is relatively regenerating. Now, there is what's known as buffer capacity. So, for example, if I add in an acid that was way too strong for the concentration of my buffer, it will blow right through it. If I added a base that was too strong, it would also blow through it. That, by the way, is what happens when you did your titrations and the color changed really quick. In the titration you did on the second one, when you guys did it, you made a buffer at the start of your titration, and then you kept adding sodium hydroxide and you blew right through your buffer. And that's why at the equivalence point, big giant jump in the pH vertically, because you made a buffer, blew through it. Now it can't stop that big change of pH, and it spikes up to the equivalence point when you did it. Now, if I didn't follow the instructions and I just kept adding acid, I could blow through my buffer, right? Because if I just keep adding acid every time I add it, I'm going to use some of the base. And at some point, I'll use up the entire base part of my buffer. And at that point, if you keep adding acid, you're now just adding a bunch of H plus into that solution. And at that point, you will see a really big jump in the pH. So whenever you make a buffer, you usually want to think about the molarity of your buffer, the concentration of your acid part of your buffer and the base part of the buffer, and the concentration of the acid or base you may be adding to it, so you don't blow through it and have these really big jumps. But that's essentially what happened again in that titration. As you were doing that titration, you made a buffer right around here, and then you kept adding your sodium hydroxide. Big jump in pH as you went up there, as you blew through that buffer. Any question on buffers? All right, that wraps up this chapter, I think. Okay, we're going to continue on here. Final chapter of the season here, chapter 17, equilibrium, which frankly, you won't see until like 1B again, I suppose. So this is a topic we're going to talk about. And again, you won't see too much of this until you get to Chem 1B, where pretty much the entire semester is about equilibrium, but they do cover it a little bit in this class. So let's get into sort of equilibrium. And the first thing we're going to talk about really, before we kind of get into equilibrium, is some of the stuff that we sort of maybe talked about in chapter 10, and has to do with reactions and reaction rates and how fast the reaction will take place. Remember that in order for a reaction to actually take place, there's a couple of things that needs to happen. We need to have an actual collision to occur. So the reacting molecules actually do need to hit each other. They also do need to hit each other sort of in the right location. And they also got to have the right amount of energy. So if you remember in sort of chapter 10, when we talked about energy, we saw some energy diagrams, and looks something like this, perhaps something like this. And we have our reactants, we have our products. Remember that hill that the reactants have to climb to get to the other side is the activation energy. And that's really sort of the minimum amount of energy is required for a reaction to take place. Reminder that not all collisions will result in products being formed. So sometimes they do collide, but not in the right spot. They do collide with not the right amount of energy to form products. So just having two things sort of come together doesn't always sort of mean that you will make products on the other side when those two reactants come together. But here, as you can see here, we got two reactant molecules colliding with each other. And remember that in this process, what has to happen here is we basically got to start breaking all the bonds, and also at the same part make new bonds. And remember that in a chemical reaction, the only thing that happens is just that basically all the reactants breaks their bonds, and all the products makes new bonds on the other side. And if you remember when we talked about sort of that energy diagram, as we go from reactants up this hill to, as we talked about, which is known as the transition state, the highest point in energy. That's what's sort of happening in this process. We got reactants breaking bonds, starting to make new bonds. And if you remember, when we get to the very top, which is the highest part in terms of energy, the transition state, we got something like this here where we have a complex where we have sort of bonds that are partially broken. We have some partially made bonds. And that's really the highest point in energy. And it's the most unstable because of that, because it kind of like breaking apart and making at the same time. And very quickly, right, once we get there, we sort of come down the hill to our products and we make our new products, which again, we didn't lose any elements along the way. We just broke bonds. Things are sort of reorganized with new things and makes new compounds on the other side. Now, how fast that occurs, or even really how slow that occurs, there are several factors in terms of a rate. And the rate really is, when we talk about reaction rate, how fast or slow something is moving. As you'll learn in 1B, when you get there, sometimes we look at reaction rates in the units of molarity, for example, per second. And then we're basically looking at how the concentration of reactants or products are changing with time. And that's sort of what we're looking at when we talk about reaction rates. Things that can affect reaction rates are things like concentration. They can increase the rate of a reaction, especially if you increase the concentration of what's reacting. Now, if you think about concentration, you think about molarity, which is a very common unit of concentration, moles of solute per liter of solution. When we increase the molarity, what that actually does is, for example, put in the solution a lot more of the solute molecules. And in a solution, that's what's reacting, is that solute part of it. Remember, a solution is two things, the solute and the solvent. And the solute is really what's reacting. So when we increase the concentration, what that does is it makes available a lot more reactants to come in contact with each other. And just by the fact that they don't have to like search around for somebody to react with will increase the rate of reaction. By the way, the opposite is true as well. If you were to lower the concentration of everybody, it's going to be probably a little bit slower of a reaction because it's going to take longer for everybody to kind of find each other. There's just not as much stuff kind of floating around in the solution or the beaker, if you want to think about it. Temperature also plays a really big role in how fast or slow a reaction takes place. Typically, if you increase the temperature, you will increase the rate of a reaction. So typically, if you increase that temperature or double the sort of, actually, if you increase the temperature by like 10 degrees Celsius for a lot of reactions, that's enough to double the rate of that reaction and allow it to occur a lot quicker. So when we increase the temperature, what we're also doing is increasing the energy in the system. And if you think about the hill that everybody has to climb to get to their side, what that does is it creates a lot more reactant molecules that have enough energy that when they collide, they're going to have enough energy to get up and over the hill to get to the other side to make products. And that usually will increase your rate of reaction. Opposite is true. If you lower the temperature, you're now going to have a lot of reactant molecules that don't have sufficient energy to get up and over that hill to the other side. And that typically will kind of slow down your reaction rate and kind of make it a lot slower. So like if you take your test tubes and you put it in hot water, usually the reaction will occur maybe faster. If you take your test tubes, throw it on some ice, it's going to maybe occur a lot slower and a lot of reactions because of that. And as we talked about here, that's sort of our energy diagram. As you can see in the reaction they showed in that picture, our reactant molecules are breaking. We're climbing this activation energy hill. We get to our transition state up on top. And again, we have that sort of really intermediate where you are breaking these bonds. And we are making new bonds here. And as we break and make those guys, very quickly is going to kind of drop down to the other side there. This, by the way this is drawn is a exothermic reaction, right? Our reactant molecules here are higher in energy than our products. So remember as well, we could tell whether or not a reaction is exothermic or endothermic. Exothermic giving off heat and energy or releasing it, endothermic absorbing it based on the position of the energy of our reactants to our products. Now, one of the ways that we talked about also in chapter 10, we're talking about energy and these sort of energy diagrams. One of the ways that we can very easily, a lot of times, increase the speed of a reaction or the rate of a reaction is to use a catalyst. And a catalyst is, again, not a reactant. It is not a product. And as it says there, it does not get consumed in the reaction. It is there really just to facilitate that reaction occurring, if you want to think about it, in a more efficient way. And because of that, that usually results in the rate of the reaction increasing. A lot of times, remember that when you look at a chemical equation, the catalyst is oftentimes written on top of the arrow. So again, sometimes you'll see something like maybe a metal like platinum written there. You may see something like H plus, which means an acid is a catalyst. But a lot of times catalysts are written there on the equation or the arrow in an equation, and that usually is what is sort of facilitating that. Now, catalysts could be like solutions, catalysts could be solids, they could be different things. We might have talked about a little bit in chapter 10 as well. Again, you could have something like a solid catalyst. And if you had gas molecules kind of flying around, what can sometimes happen is those gas molecules are attracted towards that solid catalyst. And what that just does is it just puts those reactant molecules near each other a lot more efficiently if the catalyst wasn't there, where they just got to kind of fly around and hope to come in contact with another reactant molecule. They kind of find like this kind of central location where they could kind of come in contact with each other in a more efficient manner. And that's just going to lead to a lot more reactant sort of collisions and also more products being made because, again, they don't have to kind of search around. If that catalyst wasn't there, they'd just be flying around and hope to sort of come in contact with each other. Ultimately, what that does in terms of our energy diagram, as you can see on this chart here, as we talked about, this is our sort of activation energy in red in our uncatalyzed reaction. But when we add the catalyst, because of this more efficient way of doing it, the reactant molecules really only has to climb, this hill in the catalyzed reaction. And because it's a much smaller energy barrier, that allows more reactants to have enough energy to get up and over to the other side. That leads to more products being formed, and thus the rate of reaction typically will increase. So usually when people talk about a catalyst, again, it's usually in terms of speeding up a reaction. There are actually catalysts that are used to slow down reactions. They're sometimes referred to as negative catalysts, but usually in most cases, somebody says a catalyst, they're talking about the aspect of sort of speeding up a reaction. Any questions on that there? All right, so that brings us then to equilibrium. And equilibrium is a really important sort of process that occurs. As I mentioned before, if you end up in Chem 1B, you'll talk about every type of equilibrium you never wanted to talk about. It's pretty much the entire class. You'll talk about every type of things of equilibrium processes. But equilibrium in general does deal with a certain type of reaction. So when we talk about equilibrium, it deals with a reversible reaction, and that is the type of reaction that typically has these arrows heading in both directions. So in an equilibrium process, it is a reversible reaction. And what that means is in these type of reactions, unlike kind of one-way reactions where you see a one-way arrow, different than that is these are basically kind of a two-way street. If you see an equation with a one-way arrow, it's kind of like a one-way street where reactants are definitely all going to just drop out and make products. And that's pretty much it. We're just going to kind of make products. Nobody is going back in the other direction. And in this type of reaction, in a reversible reaction, there is a forward direction of this reaction where it goes from reactants to products. And in that forward direction, what will happen is at some point, you will build up enough products that the products will decide we're going to react with each other and we want to go back in the other direction. And the products will then go back and make more reactants. And this is what's sometimes referred to as the reverse direction. So it is really like a two-way street when we deal with these type of reactions. We have reactants going to products. At some point, you'll make enough products that they will recombine and head back in the other direction. You don't really get that over here in sort of a one-way street type of situation. Now, when people talk about equilibrium, they oftentimes think about it wrongly because of the word says equal sort of in it. So when people think it reaches equilibrium, they think that they have sort of the same amount of everybody on each side of the arrow. And that's not the case. So when we talk about equilibrium, what we're really talking about is actually the rate of the reaction. And when something reaches equilibrium and reaches chemical equilibrium, what that really means is it has not too much to do with how much of everything you have on each side of the arrow. It means that the rate of the forward direction will equal the rate of the reverse direction. So when something reaches equilibrium or chemical equilibrium, we're actually talking about how fast it's going from reactants to products will equal how fast those products are then going back the other way. What that does is essentially this. When you reach equilibrium, everybody gets locked into place. So whatever their concentration is of reactants and products, they will never change. They're just locked into place. They will maintain their concentrations. If you're talking about pressure or gases, the pressures will also lock into place. So when this occurs, everyone locks into place their concentration or pressure. Now, they will be able to maintain this sort of perfect rate forever, basically, unless you decide you want to screw it up, which we'll talk about later on in this chapter. You could go and screw up the equilibrium. But one of the really interesting things about this type of reaction is you could go screw it up, but it will find a way to get itself back to this equilibrium state. So even if you try to mess it up, it will once again sort of self-correct itself and get itself back to this rate of the forward and reverse direction will equal each other, and it will get itself back to the equilibrium state. So sometimes you could actually use that to your advantage, kind of screwing up a reaction like this to get it to form certain things. And if you wanted to, you could kind of go forward and backwards a lot in this situation. But it will always sort of self-correct itself to try to get back to equilibrium. Now, one of the places where we've seen equilibrium occur, and we've talked about it, is actually phase changes. So when we go from, for example, solid to liquid, or liquid back to solid, or if we take liquid to gas, or gas back to liquid, those are the processes, right, of melting as we go from solid to liquid, freezing as we go from liquid to solid, evaporation as we go from liquid to gas, and a little condensation, right? Also sublimation and deposition as well. But these things occur, if you remember, at the same temperature. So melting and freezing, this transition occurs at the same temperature. And same thing here, this occurs at the same temperature. They are in equilibrium with each other. For example, as we talked about, if we took ice and liquid water at 0 degrees Celsius, which is the normal freezing point, melting point for water, at exactly 0 degrees Celsius, you have both things happening at the same time. You have liquid water and you have ice happening, like ice crystals. They're in equilibrium with each other. It's not until you get a little bit above zero or a little below zero that you fully transition into another sort of phase. So changes of phase is a very common equilibrium process that we've seen. And again, at that exact point, they're in equilibrium with each other. That's also why, if you remember the heating cooling curve, those spots were those sort of flatline spots, right? They don't sort of change temperature or anything like that. They're just in equilibrium with each other on one side of the phase to the other. Now, chemical equilibrium is a dynamic process where the concentrations of the reactants and products basically will remain the same once chemical equilibrium is reached. So if you had this reaction, and let's just say, for example, we had this equation here. And initially we had like 5 molar of A and 3 molar of B, and we had nothing in terms of our products. So if we initially sort of started with this sort of setup, a couple of things is going to happen in this case. And one thing that would happen is if you look at sort of the concentrations of what we have going on, we actually only have reactants available to us. There is no products at this point. So this case, there is only one way for this reaction to actually start, is it has to do the forward direction first. Because frankly, we only have reactants, we have no products. So the only way it will go is definitely in the forward position. As the forward position starts to occur, we will then start to make some products, and we'll make some products. I'll just put some rando numbers there. And we're starting to make some products. And at some point, we will actually make enough products, whatever that may be, that those guys will then come together, and that will kick off the reverse direction of this reaction. And we will now have a reaction that's heading in both directions. We will have products going to reactants, reactants going to products, until they reach equilibrium. And when they reach equilibrium, the rate of that forward direction will equal the rate of the reverse direction. And in terms of our concentrations, for example, A will have perhaps a concentration of 2 molar. B will have a concentration maybe of 1 molar. C will have a concentration of 3 molar. Maybe D will have a concentration of 4 molar. And they will reach these concentrations and equilibrium, and pretty much these guys get locked into place. They will never change again until you do something to kind of screw up the equilibrium. They'll be able to maintain that. The reason they're able to maintain that is because the rate of the forward direction will equal the rate of the reverse direction. So just as quick as you make products, those guys are just going to come back the other way. So they're just going to kind of trade places back and forth at the same rate. And that's going to mean overall, you're not going to see a net change of people's concentrations at this point. They will be able to maintain it. Any questions on that there? Now, when we look at something that has reached equilibrium, it may look to us that there's absolutely nothing happening in the beaker. So for example, let's say you mix a couple of things together and your solution was sort of colorless to begin with, the solutions, and then you mix them together. Maybe it's colorless and yellow or something like that. And you mix it together, and all of a sudden your solution turns red. And you have a red solution sitting there after you mix these things together. And to you, when you look at the beaker, you go, oh, it's over. It turned red, right? The reaction's done. There's nothing happening. It went from like color solution, maybe a yellow solution mixed together. Now I made a red solution. The reaction's over. And that is not really the case. In a sort of macroscopic sort of situation, it looks like it's static. Not much is happening. But if you were to, and if this was, say, this reaction here, my made up reaction here. And this is what turned it red when it make our products. If you were to look at this beaker sort of and to zoom in to the microscopic level where the reactants and products are, you would still have this reaction happening. You would have reactants going to products, products going back to reactants. You would have this constantly occurring. But to you, when you just look at the beaker, it just looks like it turned red, it's over. But there's a lot of activity happening below the surface, if you will, to maintain that red color that you see. And for example, you know that's the case because if this was the situation, and let's just say, this side was red and this side was more colorless, you could actually do something to this reaction once it's reached equilibrium, looks red. You could do something to this reaction to force it to go back the other way. And by forcing it to go back the other way, you could actually see your beaker go from a red color back down to maybe like a colorless or yellowish type color. And by the way, if you then decide, well, I want the red back, you could actually do something and force it back the other way. And you can basically go back and forth with these type of reactions. And depending on what is present more in these things as to what color you would see. If you ended up having a lot more reactants than products present, then you would actually see more of a colorless color. If you had a little bit more products than reactions, you see this red color. So again, sometimes the other sort of common misconception about these type of reactions are that, once you kind of see something in the beaker or the test tube, it looks like it's over, nothing's happening, but there is still a lot of activity happening to sort of maintain that. And that's sort of what we see here. Originally here, we basically have all reactants, no products. And as the reaction starts, we're going to start making some products. And in this situation, if you start with all reactants of your reactants and really no products, what you will typically see is you'll start to see, obviously, your reactants start to decrease because the forward direction will occur, and you will start to see your products start to increase. And eventually, where it reaches equilibrium is you will see both of those guys basically flatline out. And when those guys flatline out, again, what that means is their concentrations are not changing. They're just going straight, and they've reached chemical equilibrium at that point. And that's what we see here. We basically have reached equilibrium at the end. Everybody will be able to maintain those concentrations. Again, like I said, till you do something maybe to screw it up. And that is typically what you see graphically when you look at a graph of, say, reactants and products graph. You typically will see a point on that graph where the reactants line kind of levels out and the products line kind of levels out. And again, that point where they both do that, that is the point where equilibrium basically has been reached. And again, because it's just as quick as they go to products, they're going to go to reactants, and everybody's concentration will be locked into place. So concentration is again reached where that rate of the forward direction equals the rate of the reverse direction. Now, for example, if we have this equilibrium reaction in a container and we have some water plus some CO, make some H2 and CO2, and we decided that once this thing reaches equilibrium, we actually want to add some more water to it. So take a moment and think about what will happen in this particular situation. If I add more water, what will happen to the concentration of all the reactants and the products? Will they increase? Will they decrease? Will they stay the same? So take a moment and think about this. So we have this reaction, it's at equilibrium. We got a little bit of everybody in the reaction, and now you decide you want to add more water. What should happen in this situation to everybody's concentration? So take a moment and think about what you might think. Take a look. So in this situation, like I said, we have this reaction. It's sort of reach equilibrium, which does imply that we do have a little bit of reactants in the thing and products. We got everybody sort of there together. And now you decide to this container, you want to add more water. So when we take a look at the H2O, we do see that the H2O is over here on our reactant side. And what's going to happen in this case is You have now added more reactants than you have products. So what's going to happen is you now have a lot more reactants available to find each other. And if you remember, as we talked about reaction rate, the availability of reactants or guys to come together will increase the rate. So because you added a lot more reactants in this case, the reactants should not have any problem finding each other. And what that's going to do is two things. It's going to screw up the equilibrium when you do that, by the way. And it's going to now cause the forward direction of this reaction to occur because you have a lot more reactants than you do products. Now, when you cause this forward direction to occur, that's going to cause some differences in our concentrations at this point. We would now expect our H2 concentration to increase because we're now making more products, right? Forward direction goes from reactants to products. We should expect our product formation to increase. By the way, the CO2, which is also a product, we would expect its concentration to increase because of that. Now, what about the CO in this case? The CO in this case is a reactant. And when the forward direction occurs, the only way to make products is both of those reactants need to come together to make products. So what we're going to see for our CO is the concentration of CO will actually go down because the forward direction is happening. We're going to use up some of our reactants to make products. That leaves us H2O. What's going to happen with H2O? Well, kind of a weird thing will happen with H2O a little bit. Not really weird, but because you added more H2O, for the H2O, what you're probably going to see is it's going to spike up. And it's only going to spike up because you added it. But once it starts reacting with the other reactant there, once it starts reacting with the CO, we should see it start to come back down because it's now doing the forward direction. What will happen with H2O is it's potentially possible you could actually end up with more than you started with because you artificially added it. So it kind of went up high and it came back low. But the overall direction is it should also come down because the forward direction is happening in this case. So ultimately, this guy really should ultimately come down, but it may actually end up being higher than it started with only because you added it. But what's happening in this situation is we have this nice reaction that's at equilibrium, and we decided to kind of throw a little wrench into the situation. And what we did by adding the more water is we definitely caused the forward direction to occur. By the way, again, this reaction will once again come back to equilibrium where the rate of the forward direction and reverse direction will equal each other. So again, it will eventually get back to that point. But our concentrations may be different at this point than what it was when we started. Now, if we take a look at the exact same sort of reaction, but in this particular case, we decide we want to add some H2 to it. When we add some H2, that is a product over here. And what that's going to do is actually increase the products. And the result of increasing the products, much like the result of increasing the reactants was, we now going to have a lot more products available to each other than reactants. And what that's going to do in terms of our reaction is that's going to kick off the reverse direction to occur because now we have a lot more products that can find each other and start reacting, and that's going to cause that reverse reaction to occur. The result of that is in this situation, we would actually see an increase in our reactants because the reverse reaction is actually occurring, and we would see the H2O increase, we would see the CO increase as well. The CO2 will go down again because it is needed in this case to make our reactants as it's going in the reverse direction. And again, ultimately, our H2 will go down just like we saw in the previous one. Our H2 will go up because we added it. But as it starts reacting in the reverse direction, it will come back down. Again, it may actually end up higher than it started with because you added it, but that's the general thing is. So this is a clear indication or example of you could have a reaction that's equilibrium. You could actually use that to your advantage. So for example, if I was doing this reaction and I wanted to make more water, I could add some H2 to it and it's going to force that reaction to go to the left. and actually produce more water than was there originally. Now, let's just say I wanted to go the other way. I could do what I did originally in the first one, which is I could add more water and it would shoot the other way. And now I'm going to make more hydrogen gas or whatever else is over there, CO2 if I wanted to. And so you could sometimes use that to an advantage. You could add so much, for example, of say a reactant that it virtually makes this reversible reaction almost like a one-way street. It will force it always to like go to the right because of that. Any questions on what's going on here? Now, where's that button? There it is. Now, speaking of equilibrium and these type of reactions, there is a relationship that is used with equilibrium reactions. We've actually seen this relationship before when we talked about Kw, which is the equilibrium constant for water. And there is a relationship here. This is capital K, which is the equilibrium constant. And basically, to calculate the equilibrium constant, it is calculated by taking the concentration of your products divided by the concentration of your reactants. And as you can see here, one important thing of that is the coefficients in the balanced equation become the exponents when you do that. Once again, here, the concentration symbol is molarity in most cases. And again, these coefficients are used as those exponents when you do that. By the way, when you do this for concentration, this is also sometimes referred to as the Kc value. C for concentration. Just like Kw has to do with water, yeah? And if you take 1B, you'll learn about Kp, Ka, Kb, Ksp, Kf. I could keep going, but it's like all the K values you never wanted to know. Chem 1B is brought to you by the letter K, basically, is all the K values that you learn. Now, by the way, this should be a capital K because that's the equilibrium constant. Lowercase k is actually the rate constant, which is something to deal with kinetics that you also learn in 1B as well. But capital K is here. Now, products over reactants, if you do it with concentration, that again, as I mentioned, is what is sometimes referred to as the Kc value. By the way, you could do this if these were all gases. So if all these guys were gases, you could write an equilibrium constant that dealt with pressure, where you would take still products over reactants, the partial pressures of each of these guys if they were gases. And because these are dealing with gases and pressures, that is what is sometimes referred to as the Kp value. P, again, meaning you did it in pressures. And this would be pressures. And usually atmospheres is the unit that you would use for that sort of thing. Now, what is the K value really tells us? It is the equilibrium constant. It is a couple of things which are kind of nice. It is basically just a number. So there are no units associated with the equilibrium constant. And what does it actually tell us? Well, I'll go this way here. Yeah, I'll go here. Maybe. When we look at the equilibrium constant, if we have a really large value or a small value, it tells us a couple of things. So if we just think about our equilibrium constant, which is basically our products divided by our reactants, obviously using the exponents to from the balance equation. If you have a large value of K, what that means is when you reach equilibrium, you mainly have products present, right? Because if I take a large number on top divided by a small number, I will get a large number for K. And if you have a small value of K, that means that when you reach equilibrium, you mainly have reactants present. And that's because if I take a small number divided by a large number, I will end up with a small number. What's considered a large number? What's considered a small number when you're looking at the K value? Well, clearly the K value of 1 is considered large. So if you have a value of 1 or above, it is considered a large value of K. And you would expect when that thing reaches equilibrium to have more products than reactants. If you have a small value of K, that should be less than 1. And when you reach equilibrium, you should expect perhaps more reactants being present than products. There is definitely extremes to this. You could have an equilibrium constant that's like times 10 to the 54 power, which is super large, which means you pretty much have all products, no reactants happening in that case. You could have a really, really small value of K, like to the minus 34 times 10 to the minus 34, which basically means you got all reactants. That reaction is really not occurring. So there are different, and anywhere in between, those sort of numbers, you could have ones that are, really large numbers, really small numbers. And like I said, it's anywhere in between as well. You could have those values. But that is what K kind of tells us. It tells us, again, if we have a large value, I should expect products at equilibrium. If we have a smaller value, you should expect reactants to be present. Now, here again, if we take a look at an equilibrium guy, we would write our expression, again, going to take our products divided by our reactants. And again, it's important, as you see here, to use the coefficients as the exponents. So that's where the 2 comes from, is the coefficient in the balanced equation. Concentration of NH3, which is our product, divided by the concentration of N2. By the way, the coefficient here is 1, which is why you don't see anything written there for 1. And the coefficient here is 3 divided by the concentration of our H2 squared. In order to put numbers into an equilibrium expression, they have to be equilibrium concentration. So they have to be equilibrium concentrations or equilibrium pressures to go into here to actually get a number. Once again, as I mentioned before, this would be considered a Kc value for concentration, is what C stands for. These are all gases. As I mentioned a second ago, you could actually write a Kp value. Again, works the same way. You're going to go products, which is this guy. So the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure cubed, because of the coefficient, of H2. And again, this is a different type of equilibrium constant. They both will tell you the exact same thing. It doesn't really matter what the little subscript on the K is, if it's Kp, Kc, Kw, A, B, C, D, E, F, G, whatever you want to be. They're basically all products over reactants. I will say, as you'll learn in 1B, in most cases, the Kp value and the Kc value are not usually numerically the same value. They can be, but a lot of times they're not, but they will tell you the same thing. So if you have a large Kc value, you probably will have a large Kp value, and vice versa. If you have a small Kc, you'll have a small Kp value. Now, K always has the same value given the temperature, regardless of reactants and products. So a very hard thing for people to understand when they're doing equilibrium and dealing with K is basically this idea. So let me just explain it a little bit more to you. First off, K is dependent on temperature. The absolute only thing that could change the value of K is if you change the temperature. If you keep the temperature constant, no matter what you do in that equation, you should always end up with the same K value. So what I mean on that is if we had this equation, our A plus B goes to C plus D, and let's just say we did an experiment, and we're going to do all these experiments at 25 degrees Celsius. And I did experiment 1, and I started this reaction with 4 molar of A and 2 molar of B and nothing of C and nothing of D. And I calculate my K value, and I'm going to say my K value is going to be 10, just making up, obviously, the number here. Now, I did experiment 2, and maybe I started with 2 molar of A and 1 molar of B. Maybe I had a little bit of some products there as well. Maybe I had 3 molar of C and 2 molar of D. I could calculate my equilibrium constant for this reaction, and it will still be 10. It will not change, even though I started with some reactants, some products. Heck, I could even do a third experiment where I don't start with any reactants, but start with all products. And I could calculate my equilibrium constant, and it's still going to be 10. Now, you may be saying to yourself, how could that be if I started with different amounts in each of those experiments? How do I end up with the same equilibrium constant? The answer is a pretty simple one. We're looking at the proportion of products to reactants. So let's just take a math problem where I want my K value to equal 2, right? Now, there's many different ways I could get to the value of 2. I could have a ratio of 4 divided by 2 would give me 2. I could have an equilibrium ratio of 8 divided by 4 would give me 2. I could also have an equilibrium ratio of 2 divided by 1 would give me 2. All of those have different sort of ratios of products to reactants or concentrations of products to reactants, but they all end up in the same ratio of products to reactants. And that's what's happening here. Because the rate of the forward direction and reverse direction when they reach equilibrium will always result in the same proportion of reactants or products to reactants. And you'll always get the same value of K regardless of what you start with. So if you want to start with all products, you could do that. You want to start with all reactants, you want a little bit of everybody, you could do that. When that reaction comes to equilibrium, it'll always come to equilibrium at the same ratio of products to reactants. First off, any questions on that there? So what do we mean when we talk about if you change the temperature, you will get the different value of K? What we mean by that is if we did the exact same 3 experiments here, 1, 2, and 3, for this exact same reaction, but we did it at 45 degrees Celsius, we would get the exact same K value for every experiment we did, but the K value in this case may be like 40 instead of 10. And when you compare the K value at 25 degrees to the K value at 40 degrees for the exact same reaction, they will be different values. But if you compare all the K values at 40 degrees for all the experiments you did, they will all be the same. And if you compare all the K values at 25 degrees for those 3 different experiments, they will all be the same. But in comparison of 2 different temperatures, you will see differences in the K values. Any questions on that there? So again, temperature is the only thing that could actually change the value of the K. And again, comparing from the K value at one temperature versus another is what we're looking at there. All right, so let's take a look at this here. We have a reaction, which is really our weak acid, acetic acid, breaking apart into acetate and H+. We could write our equilibrium expression, which once again is going to be our products over our reactants. And in this case, that is H+, so our K is going to be H+ concentration. It is to the first power, so we don't have to do anything. This guy is going to be our acetate. Also to the first power, divided by our acetic acid, which is also to the first power as well. And that would be our equilibrium expression. Now, when we talk about equilibrium expressions, there are basically 2 things that you include in it, and there's really 2 things that you don't put in it. So when you're doing a K expression and you're writing it, we do not include anything in the equation that is a solid or a pure liquid. So anything that has an S or an L next to it, we do not put into the equilibrium expression. What that leaves you is basically 2 things that go in. We do include anything that is in the gas state and anything that is in the aqueous state. So if you have something that is aqueous, you put it into the expression. If you have something in the gas state, you put it into the expression. But if you have something that is solid or liquid, we do not include it. 2 reasons really for that is a solid is basically just sitting there. if you think of like if you threw a rock into a beaker, maybe don't throw the rock into the beaker, put it in gently into the beaker. The rock is basically just sitting there on the bottom. It's really not participating or doing much in the solid state. So things in their solid state will not have any effect on the equilibrium reaction sort of occurring. Also, things that are pure liquids like water, for example, in the liquid state, their concentrations are so high that they really don't change all that much. They remain relatively constant throughout the process, so we don't include them. So anything with a G or an aqueous symbol should be included. Anything with an S and an L you should leave out of the expression. Any questions on that there? Come here. Where's that button? There it is. Now, if we wanted to calculate an actual value, as I mentioned before, you would need the equilibrium concentrations. So here, these are going to be our equilibrium concentrations that are given to us. And in this class, they would be given to you. When you go to 1B, you'll learn about how to calculate them yourselves. But we would start with here our equation, and we would write our equilibrium expression, which would be the concentration of our products, which is NO2 squared, again, because of the coefficient, divided by our reactants, which is N2O4. Now, since they gave us our equilibrium concentrations of each of these, we can put it in. So we'll take our NO2, which is 0.06, and again, we got to make sure we square it, divided by our 0.055, and hopefully they have the right one circled there. Let's see. It looks like 0.065, which looks right there, so that's good. 0.065 would be our equilibrium expression. And once again, as I mentioned, it does have to be equilibrium concentrations to go into this. By the way, if you were dealing with pressure, it would have to be atmospheres typically that go in here, but equilibrium pressures as well. As I mentioned earlier, there is no units associated with K, so it is just a number. So we don't typically use units with it because a lot of times, honestly, they don't really cancel out all that great. So typically we just use a number. This would be considered a small value of K. And that would mean that when we reach equilibrium, we would expect to mainly have reactants in this case when we do reach equilibrium. All right. So as I sort of stepped upon a little bit earlier, what we've been sort of talking about up until this point are really sort of homogeneous equilibrium. And homogeneous equilibrium, much like homogeneous mixtures, means it's the same throughout. So when we talk about a homogeneous equilibrium, that means everybody in the reaction, they're all in the same state. So everybody here is all in the gas state. Everybody here is all in the aqueous state. They are homogeneous equilibriums. And again, in each of these cases, we could write our expressions. As we saw earlier, this would be our K is our NH3 squared divided by our reactants, our N2 and our H2 cubed. For our second one here, our K expression would be our products, our H plus concentration times our CN minus divided by our HCN. Once again here, everybody would be included on each of these because they're all gases on the first one, they're all aqueous on the second one, so we do include them for sure in the expression. Now, as I mentioned a second ago, when we get into heterogeneous equilibrium, much like a heterogeneous mixture where you see different sort of layers and stuff, here everybody's in different phases. They're not all in the same phase. So you can see here we got some solids, we got a gas, we got some gases, we got some liquids. And when we do this, as I mentioned a second ago, it is that solid and liquid that are no-goes for our expression. So we do not include those in there. So if we were writing the expression here for the first one, our K expression, our equilibrium constant expression, would be the concentration of O2 cubed. This would not be included as it's a solid, nor would this one be included in there because, again, it's a solid. So really the equilibrium here is really just based on kind of the O2 is what's happening. When we come to the second one here, our equilibrium will be our H2, which is our product, again squared because it will be included, times our O2 in this case. And once again here, water, which is a pure liquid, would not be included in the expression. So this is just the products in this case. And that sometimes happens. Sometimes it's just the products involved. Sometimes it's the products and the reactants involved in the expression. And it's possible to have just reactants involved. So hypothetically speaking, if you had something like maybe A that's aqueous to maybe B that is a solid. If we were going to write the equilibrium constant on this, we would not include our products. So in that case, we would actually do 1 over our reactants. And again, because the product is not included, this guy would be included. So if your products are not included, just go 1 over the reactants is how you would write the expression. Any questions on that there? So the position of the heterogeneous equilibrium, as I mentioned, really not dependent on solids or liquids. The concentration in liquids and solids remain constant. Really, the only way for a solid to sort of participate is it would have to dissolve, and then no longer would be a solid at that point. It would be aqueous ions, and then it would participate. So here, if we look at this, looking at this reaction, we're going to write our equilibrium products, which this would be included. So calcium, this guy, which is aqueous, would also be included, which would be F minus, again, squared. This guy, which is a solid, would not be included. And we would get basically the concentration of calcium times the concentration of fluoride squared. Again, when you get to 1B, you will recognize this as what is known as a KSP, which is known as the solubility product. KSPs is basically the equilibrium constant for things. If you remember your solubility rules, things that are insoluble. So when you look at something on your solubility rules, it says this thing is a solid. Even though it is a solid based on solubility rules and you expect a solid to form, it will still break apart a little bit into solution as ions. Everything has some degree of solubility and actually will set up an equilibrium like this. So even though based on solubility rules, we would expect this guy to be a solid, in reality, in solution, you have a very, very super small amount of the free ions still floating around, and it actually sets up this equilibrium in the solution to do so. KSPs, for example, are K values that typically have very, very small values, like to the minus 34, minus 54, and that's because they are mainly insoluble and will break apart and stay together, and will stay together. Now, as I mentioned, what we're going to talk about next here is Le Chatelier's principle. And as I mentioned earlier, if you do have a system that's at equilibrium, you could actually do something to it to, frankly, screw it up, I guess is the way you can say that. And what happens with these reactions, as I've been mentioning, is they will basically try to self-correct themselves. So when we talk about Le Chatelier's principle, we have a system that's at equilibrium. So you have this situation here. This guy's nice and happy. He's at equilibrium. And he's number 1 here. And he's perfectly fine. And again, what that means is at this point, the rate of the forward direction will equal the rate of the reverse direction. You decide to do something to this equilibrium to stress it out. You add a stress. Nobody likes stresses, but you add a stress to the system, and it's going to kind of mess it up and stress it out a little bit. And when you add a stress, it will mess up the equilibrium. That's a very scientific way of saying that. It will mess it up. Yeah. And let's talk a little bit about what stresses are. Stress could be something to do with the concentration of reactants or products. It could do something with pressure and volume if you're dealing with gases. You could do something with temperature. You could do something with like a catalyst. So you do something to this reaction that frankly stresses it out. And what that's going to do is cause the equilibrium to no longer be. You're no longer going forward direction, reverse direction equal to each other. And it will cause this equilibrium to basically get messed up and want to get back to equilibrium. So this will cause the stress, so it'll mess up the equilibrium. It will want to get back to equilibrium. And there's basically three ways, in a sense, it could get back to equilibrium when you talk about Le Chatelier's principle. And that is, it will shift to the right, it's very commonly referred to, which means you're going to go and make more products, basically. You can go to the right-hand side of the equation. It may shift to the left, which means you're going to make more reactants. And then no matter what happens, there is certain situations that even though you did something to screw up this equilibrium, it will actually cause nothing to occur, even though you did something to it. And you can have a no change occur. And basically, when it sort of self-corrects, this reaction at the end will come back to equilibrium, number 2, and be back to the rate of the forward direction, and the reverse direction will equal each other. And this is the idea of Le Chatelier's principle. System at equilibrium, you do something to it, messes up the equilibrium, it self-corrects itself to get back to the rate of the forward direction and reverse direction equaling each other. So let's talk about each of these sort of stresses and what happens when we apply them. So the first thing we're going to talk about is concentration. And basically, there's two things you could do with concentration. You could either add more or you could remove. And when we add more, it will always shift away from the side we added it to. Now, when we talk about sides, what we're talking about is the actual balance equation. Yeah. So when we talk about kind of left-hand side, right-hand side, shifting to the right, shifting to the left, we're talking about the actual equation. Left-hand side of the equations are reactants, right-hand sides are products. And in this case, if you add more reactants, it will shift away from the reactant side, go to the products. If you add more products, it'll go to the reactant side, shifting away from it. If you remove, it will add, I'm sorry, not add, it will shift towards the side you removed from. It will shift towards the side you removed from. So let's just take a nice little example of this. Let's say we had a reaction that was at equilibrium, and I'm going to represent that on a seesaw here with some quality drawn stick figures. They're quality stick figures, they have faces. And over here, we'll call this guy, that side, the reactant side, this side, the product side over here. And at this point, we're at equilibrium. Nice and happy. We're going back and forth. Everybody's at equilibrium. And let's just say in this particular case, we decided we're going to add somebody to the right-hand side. And if we add somebody to the right-hand side, this is what's going to occur. We're going to end up with this situation here. And clearly we have screwed up the equilibrium by putting some more stuff on our product side. Now to fix this, do I need more people on my product side or reactant side? I need more people on the left-hand side here. So it's going to shift away from the side I added to the other side. And that's going to cause this equilibrium to come back to equilibrium, or this system to come back to an equilibrium state by shifting away from it. And now we're back to equilibrium at this point. So if we add, as we did here, more products, we're going to cause a shift to the left there and make more reactants to come back to equilibrium. Why does that really occur? It really occurs for something that we talked about earlier, which was in this particular example with my stick figures, I added more products. That's going to cause the reverse reaction to occur. And that is why it's going to send in this direction, because we now have more products than reactants. And that's going to cause formation of more reactants and use up some of our products. And that's going to bring us back to an equilibrium state. Now, what happens if we did kind of the same idea here with our system at equilibrium to begin with? And we decide the guy on the right-hand side here decides he's had enough for today. He's going to hop off. He's going to get off the seesaw here. If he gets off the seesaw here, this is what's going to happen. And obviously we screwed up the equilibrium now. And again, to fix this, we don't need more people on the left. We actually need more people on the right-hand side. So we're going to shift towards the right here to balance it back out. And it will balance back out now and reach equilibrium again. Will it be the same equilibrium as before? No, but it'll be back to the rate of the forward reaction equals the reverse reaction in this case. Why does this happen? This happens because when I remove my products, you could think about it one of two ways. Probably the easier way to think about it is when you remove your products, you made a big hole over there. You got to go fill the hole. So you got to shift towards the hole you made and you want to fill it. The real reason is when you remove your products, you now have more reactants than you do products. And because you have more reactants than you do products, it's going to cause the forward direction in this reaction to occur, and it's going to actually go towards the product side. So if you remove products, it will shift towards the product side. If you remove reactants, it will go towards the reactant side. If you add reactants, it will shift to the product side away. And if you add products, it will go to the reactant side away. So AA, add away. And when you remove it, you want to fill the hole, whichever side you removed it from. It's a good way to kind of remember that. Any questions on that there? The next sort of thing that can affect it is dealing with pressure and volume. And they typically are sort of grouped together. And when we talk about pressure and volume, this is usually involving a gas equilibrium where you have gas molecules involved. And if you remember pressure and volume, our friend Boyle said that as pressure goes up, volume goes down. And that's the relationship that occurs here. If I increase the pressure, the volume is going to go down. And because I now have in a smaller volume gas molecules, I don't want the pressure to go way up. I need to actually shift to the side with the least number of gas molecules. Because basically the change that occurred is the pressure went up. So I want to kind of bring the pressure back down. And if I put more gas molecules in that small volume, the pressure is going to continue to go up. So I need to go to whichever side has the least number of gas molecules. That depends on the actual reaction you're looking at as to which side has more or less gas molecules. You basically just have to count up the coefficients for anything with a G and figure out which side has more or less. If you have the pressure going down, the volume will go up. So the change that's occurring in this situation is the pressure is starting to drop. I want to bring it back up. To bring it back up, I would need to shift to the side with the most gas molecules. And what that's going to do is put more gas molecules in this bigger area, and that's going to cause more collisions and bring the pressure back up. Once again, it is dependent on the equation you're looking at as to which side that is, but you have to sort of figure it out. So let's take a look at one. Let's say we had 2A plus 3B goes to, I go with 3C in this case. These are all gases. All right, let's see here. What will happen? Will it shift to the right, to the left, or no change if I do the following things? I'm going to add some C. I'm going to remove A. I'm going to increase the pressure. I'm going to increase the volume. I'm going to add more B. All right, so take a moment for each of those to this equilibrium. I'm going to do those things, and what will happen in each case? Will it shift to the right? Will it shift to the left? Or will there be no change that occurs? Okay, so let's take a look here in the first. We're going to add some C. So what you want to think about is where C is at. C is over here on the product side. Remember that when I add, it goes away. AA. So I'm going to add product side. That's going to cause it to shift away from the product side to the left-hand side. And again, the reason for this is when you add more C, you have more products than reactants. It's going to cause the reverse reaction to occur, and it's going to go to the left in this case. Now I'm going to remove A. A is over here on the reactant side. When I remove A, again, you can think about it as you made a hole on that side. So you want to fill that hole. So we're going to shift to the left. Again, the real reason for this is when you remove the reactants, you now have, again, more products. And that's going to cause the reverse reaction to occur. And that's why it's going to go to the left in this case. Now, the next one here is I'm increasing the pressure. I personally, when I talk about pressure and volume, I always think about it in terms of volume. So when the pressure increases, that means the volume will decrease. And when I have a smaller volume, I need less gas molecules. So in this case, that is a grand total of 5 gas molecules on the left-hand side. 2 and 3 is 5. And on the right-hand side, we have 3 gas molecules. So in this case, because we need smaller gas molecules, it's going to shift to the right. So when you're doing that one, you can think about volume. Small volume, less gas molecules. Big volume, more gas molecules is a way to kind of remember that. Any questions on those there? Coming here, increasing the volume means that my pressure will actually go down, but increasing the volume means I'm going to have a bigger volume. So once again, larger volume, more gas molecules needed, going to shift to the left in this case, where we have 5 gas molecules versus 3. And lastly, adding more B. B is a reactant, again, going to shift away, going to head toward the right-hand side in this case, again, causing the forward direction here to occur because we have more reactants than we do products. So that's going to cause that forward direction going to the right to occur. Any questions on any of those there? All right, so now that we talked about pressure and volume, the last couple of things that can affect Le Chatelier's principle is temperature. And the good news about temperature is it works the same as concentration, which means if you increase the temperature, it should shift away. And if you decrease the temperature, it should shift towards. Now, the important part of this is how do you know which side the temperature is on, right? Is it a reactant or a product? So this has to do with something else that we talked about in an earlier chapter, and that's our friend exothermic reactions and endothermic. In an exothermic reaction, heat and energy is released. So when we look at it in an equation, not correct in all aspects, but we think of heat and energy as a product. So if you have an exothermic reaction, you should think of energy as a product. Remember, there's a couple of ways that we could very commonly figure out, is this reaction exothermic or endothermic? Throw back from the past, our delta H value being negative is the most common way that we know, or they just tell you it's exothermic. But if not, they very commonly will give you a delta H value with a value that's either positive or negative, negative being exothermic. Endothermic, heat is going to be absorbed. And in this case, that is considered a reactant when we have that type of reaction. And also, delta H would be a positive number. So if you have a exothermic reaction versus an endothermic reaction, that's the first thing you want to sort of figure out when you're dealing with temperature rising or decreasing in Le Chatelier's principle. You got to kind of figure out, which one you're dealing with. Then at that point, you could just roll with the normal if you're increasing away from the side you're increasing, if you're decreasing towards the side. Any question on that there? Last thing that could affect it is a catalyst. And the deal with a catalyst is it really won't do much. It will get you to equilibrium quicker, but you'll actually get a no change. And that is one of the ways that you could kind of get a no change in this situation, Le Chatelier's principle. By the way, the other place you could get a no change is gas molecules. So if you count up your gas molecules on each side and they're both the same, there is no higher or lower gas molecules. That also will cause a no change. So equal numbers of gas molecules will sometimes cause a no change. Adding a catalyst will cause no change. Last one that sometimes pops up with Le Chatelier's principle and no change is noble gases. You add a noble gas to a sort of thing. Again, they're chemically inert. That will also cause a no change. So those are kind of the three ways that sometimes you can get a no change to sort of occur. Any questions on that? So if we have then, we'll do this one here. Yeah, go 2 there and 3 there. And just for the sake of this, we'll just make up a number. It's not the right number. We'll make this 125 kilojoules is our delta H. Negative 125 kilojoules. Definitely not the right one for this one, but we'll go with it. All right, so what we want to know in each of these cases, are we going to, again, shift to the left, shift to the right, or no change? All right, we're going to add NH3. We're going to decrease the temperature. We're going to increase the pressure. We're going to remove N2. We're going to add some H2. Again, we're going to decrease the volume. We will add a catalyst. All right, let's take a moment there for each of those, decide which way are we shifting here. Okay, so let's take a look. So here we're going to add some NH3. So we're adding over here to our product side. Again, add away. So we add it to the right is going to cause the reverse reaction to occur, and it's going to shift away from the side we added it to. So it's going to go to the left. We're going to decrease the temperature. So again, when we're dealing with temperature, it does work the same way as concentration, but we do need to determine endothermic or exothermic. And again, here we do see a delta H value that's negative in this made up one. And because of that, that means in this one, it would be a exothermic reaction, where if we were to put the heat or energy into the equation, it would serve as a product. And now that we know it's on the product side, I'm going to decrease it. Remember that when we remove it, it will create a hole on that side that we need to fill, and it will go towards the hole, and it should shift to the right in this case. Obviously, if we increase the temperature, it would do the opposite. It would shift to the left. Any questions on that one there? Increasing the pressure, again, related to volume, means the volume is going to go down. Once again, thinking about volume as the main thing here. Small volume, less gas molecules is what we need in this case. So overall gas molecules on the reactant side, we have 3 there and 1 there is 4 gas molecules. On the product side, only 2 gas molecules. So in the smaller volume, we will need less gas molecules. It will shift in this case to the right, which has only 2. Again, you're just basically going to count up the coefficients for anything that has G's on each side is the best way to do that. Here we're going to remove N2. N2 is on the reactant side, again, creating a hole over there that we need to fill. And again, basically what that's happening is we now have more products than reactants. So the reverse reaction is actually occurring in this case. We're going to add some H2. H2 is over here. More reactant is going to cause the forward direction to occur, and it's going to shift away from the side we added it to. Decreasing the volume here is actually the same thing I did here. Look at that. So it should also go to the side with the least number of gas molecules, which would be to the right. And lastly, adding a catalyst will cause no change, basically, to occur. Any questions on any of those there? So when you're thinking about Le Chatelier's principle, really the thing you want to think about is what I just did, is that going to cause the reverse reaction or the forward reaction to occur? And that will tell you basically which way is going to shift. Any questions on Le Chatelier's principle? All right, that wraps up this chapter, what we're going to talk about, and Chem 3 for the season. Congratulations.